All right, so in this video, we're covering the equations for lines and planes in space. We're just going to give the equations, one example of each, and then we'll look at more variations of these in the homework problems we do in class. But I want to start out with a line. So we did cover this in lecture this last week. But we're going to let capital L denote a straight line in space. And so we want to describe L by an equation or a formula. To do that, there's sort of two pieces of information that we absolutely have to have. We need to know a point that is on the line. So in this case, I'm going to call this point P, and it has coordinates x0, y0, and z0. So in a given problem, you'll have to figure out what these values are. And then we also need to have a vector v that runs parallel to L. And so V is going to have to be, here the components for V are just going to be V1, V2, V3. Again, we'll have to actually find an explicit vector to come up with an equation. Now notice that neither this information nor this information is unique in the sense that a line has an infinite number of points on it, and given one vector that's parallel to it, any non-zero scalar multiple of that vector is also parallel, and therefore neither P nor V is unique. But often the problem that we have, the way it's stated, will give us sort of natural choices for P and V that may be the easiest things for us to find. And so the equation for a line is not unique. You can describe the same line by various equations, and each of these choices will represent a different parameterization of that line. Okay, so the first form is the vector form for the equation of the line, and it goes like this. So the points on the line L are given by the vector-valued outputs of the following function. The function is this function here, r of t. The vector arrow that's over r is indicating that this function is a vector-valued function. That means the output of this function it outputs a vector. The input, this variable t, is a real number, and so this inequality on the side is just saying that t is going to run over all real number values. In other words, the domain of this function is all real numbers. And r of t is a function that takes in a real number t and spits out this vector output, which is the vector OP, where O is the vector that runs from the origin in 3 space as its initial point and has terminal point P, that P that was found up above here that was on L, and plus T times this vector V that's parallel to our line. So what this function does is it outputs a whole bunch of vectors, and each vector that it outputs has the form, the vector that goes from the origin to P, plus some scalar multiple of that parallel vector V. Now, the second equation down here, all we're doing is we're taking the components of the vector OP. So since OP runs from the origin to P, in component form, its components are just the coordinates of P. And then we've just thrown in over here the components for V, which this is just how we had initially described V, as a vector having these components. All right, so let's work out an example here. So let's say you were interested in finding the equation of the line that goes through the point P equals 0, 2, 0, and Q equals 1, 1, 1. Well, you could choose either P or Q to be the point on the line. So we'll go ahead and pick P since it was listed first. That'll be our sort of chosen point that's on our line. And since the line goes through those 2 points, an easy parallel vector to find to this line is just the vector PQ. And remember that when you're taking a vector starting at P, ending at Q, the components are just take the coordinates of Q and subtract away the coordinates of P. And so we get this. So we get the vector 1, minus 1, 1. And so since this is the vector or a vector that's parallel to our line, and we're choosing P to be a point on the line, the equation for our line is given by this right here. R of t equals 0, 2, 0 plus t times 1 minus 1, 1. Now I have sort of two notes written here. There's two different things, at least two different variations we could have made here. So the first note says, had we chosen Q instead of P to be the point that we were going to use on our line, then the difference would have been instead of 0, 2, 0 being the vector that we start with, that's the vector from the origin to the point on our line, we'd have had the vector 1, 1, 1, which would have been the vector from the origin to the point Q. So that would have changed the front part if we had wanted to use Q instead of P, and then we would have gotten this form of the equation. The next variation says, well, alternatively, we could have also used the vector QP instead of PQ. Now, what's the difference between QP and PQ? Well, QP runs the opposite direction of PQ. So it's just minus PQ. So the components of QP would be minus the components of PQ, therefore minus 1, 1, minus 1. And so we would have gotten this form for the equation of the line if we had used Q as our preferred point and the vector QP as our parallel vector. And so the note down here at the very bottom is this gives the same line. In other words, as this input variable t runs over all real numbers, the vector valued outputs you're going to get in each case will be the same set of outputs, but they will correspond to different input values of t. In other words, in all three cases here. And so we'll talk more about that in class. The parametric form for the equation of a line. So let's go ahead and say that our line L, let's suppose we already know what its vector form of its equation is. Okay, so this just goes back to the previous slides. Then the parametric form comes by taking, if I took the components of this vector, if I took this t that's scaling this vector here, and I, knowing that when we scale a vector, you just multiply each component by that t. If we did that and then we added the two vectors, the components we get would be these three expressions down here. And so the parametric form of the equation of the line is to take our three coordinate variables, x, y, and z, and have three equations for each one of them. One equation for each, so three total equations. X equals x0 plus tv1, which is what you would get by adding that, plus t times v1. And then in a similar way, y equals y0 plus tv2, and z equals z0 plus tv3. Okay, we move to planes in space. Now, to describe a plane in space, you need very similar information to what we needed for a line, slightly different. To do this, we need a point P that is on our plane, and we need a vector n that is normal to the plane. In other words, that is also, being normal is the same as being perpendicular or orthogonal to the plane. So in other words, every vector that's in the plane would be perpendicular to this normal vector little n that points up out of the plane. Now, I'm going to give you a little bit of an idea behind how we derive this formula I'm about to show you on the next page. So let's take, so P is our point that's on our plane, and so let's just draw it right here. It's literally right there. So that's our point P having coordinates x0, y0, and z0. Let's suppose I want to know which points in space are also on this plane. Let's take a point with coordinates x, y, z. How do I check to see if that point is on this plane? Well, the idea is I'm going to take the vector that goes from P to this generic point with coordinates x, y, z. This vector needs to be perpendicular to the normal vector n for this point to be on the plane. And this is precisely the condition for a point to be on this plane. A point is on this plane if and only if the vector that goes from P to that point is perpendicular to, orthogonal to, this normal vector n. Well, how do we check for perpendicularity? We check for it using the dot product. We already saw that in section 12.3. Two vectors are perpendicular if and only if their dot product is 0. And that's where we come, so we get three equivalent equations for that plane. And the first one is the vector form of the equation, and here's what it is. We take the vector from P to that generic point having coordinates x, y, and z. That vector has components x minus x0, y minus y0, and z minus z0. And we dot it with the normal vector n, and we set that equal to 0. All right, so that's the first equation. That's the vector form of the equation for the plane. The second equation is what we get when we actually carry out that dot product. When we dot, what are we doing? Well, we take the first entry here, and we multiply it by the first entry there. Then we add to that the second entry times the second entry, and then add to that the third times the third, and that gives us these three expressions here. Now notice that all I've done is I've sort of turned around. Instead of x minus x0 times a, we've written it a times x0, sorry, x minus x0. But there's no issue there because the multiplication commutes. And so we get this second equation. So I believe the book calls this the component form of the equation of the plane. And it very, very clearly and immediately comes from that vector form above. And then the third form, all this is you multiply out, distribute the multiplication on these three terms here, collect the ax plus by plus cz all on one side, and then set them equal to d, where d is just the stuff you get here. This is just what you get when you distribute this multiplication and add everything to the right that's a constant. Now notice a, b, and c are going to be actual numbers. They're the components of the normal vector you found. x0, y0, and z0, they're also numbers. They're the coordinates of the point you found on your plane. And so everything over here is in fact a constant or a real number. All right, so example, the equation for the plane containing the point P equals 2, 1, 3 and having normal vector n equals 7 minus 2, 5. Well, just using the last equation, the middle equation from the last page, you would get 7 times x minus 2 right here, plus minus 2 times y minus 1, plus 5 times z minus 3 equals 0. And we could multiply that out, add all the constants to the right, and you get 7x minus 2y plus 5z equals 27. So this is the form of the equation. I'm sorry, let me go back. Form of the equation for a plane. And again, we will do lots of examples to show how this works.